Hi, this is going to be some extra AC power problems. So, a certain appliance can be modeled as a resistive component, a resistor in series with a reactive one, a capacitor or inductor. When plugged into a wall outlet, the appliance draws a complex power of this. How much real power is the appliance using? Well, the real power is just the real part of the complex power. So that's 240 watts. What's the reactive power supplied? Similarly, Q is negative 500 volts amps reactive. What's the average power used by the appliance? That's just another way to say real power. So that's also 240 watts. What's the appliance's power factor? Now this is a little bit more complicated. So here is here's the idea behind this. The complex power we know is P plus QJ. And the other thing we know about it is that it's equal to its own magnitude. Maybe we'll give that just the symbol S times the cos of theta Z plus J sine of theta Z. So kind of like S e to the J theta Z. That's kind of where the complex power comes from in terms of the phase difference between the voltage and the current. So using any of this stuff, once we've got the complex power, you can rearrange and say, all right, theta Z, let's see, tan theta Z would be equal to sine theta Z over cos theta Z, which is what you'd get if you were to take the same thing multiplied by, let's say, S and S there, and that is just Q and P. Okay, so that means you can get theta Z by taking the arctan of Q over P. And then once you've got that, you take the cos of that in order to get the power factor. Okay, so let's get some calculation going. We're going to need to write out what S is. Why don't we write out P as 240 and put a decimal there to force floating point stuff later. Q is equal to negative 500. And then we've got S is equal to P plus Q times I. Okay, looks good. Then we can say that theta Z is equal to arctan of Q over P. There we go. And then the power factor is the cos of theta Z. Okay. So we've got, looks like 0.43. And since theta Z is negative, this means that the current is ahead of the voltage. So that means this power factor is leading. Okay, apparent power, that's the magnitude of S there. And for that, we can also just use our calculation here. So we've got 554.6. And we can put that in watts. Draw the electrical model of the appliance, writing all component values. So figure out what we have, whether it's like a resistor and a capacitor or inductor. Before we do this, I'm going to jump around in the questions a bit. Later on, it's asking us to find out the phase angle of the voltage relative to the current. So we've got that. That's theta V minus theta I. That's exactly what theta Z is. And that we said was negative 1.12. And that's in rads. Okay, now we need impedance, and then we need to know Right. Okay, so this question here is asking us about the current phasor and the current through the appliance. So basically the strategy is going to be, since we have to find the current and the impedance and the component values, so the resistance and the inductance or capacitance, then the easiest thing to do is first find the current and then use that to find the impedance and then use that to find the component values. So yeah, let's go about that. So we've got S is equal to V RMS times I RMS star, which means that I RMS complex conjugate is S over V RMS, and then you can take the complex conjugate of both sides and say that I RMS is S star over V RMS star. All right, so let's put in our V RMS, and that's just 120. So that means that I RMS is the conjugate of S over V RMS. And that's 2 plus 4.167 J amps RMS. Okay, that's the current phasor. And while we're here, I guess we can figure out what the current is. So you could find I RMS by taking the absolute value of this. And the phase of it. But another way to do it, if you want to check, is by taking the apparent power and dividing by V RMS. So let's check what that is. And we get the exact same value. We've already figured out that the current phasor has a phase of positive 1.12 relative to the voltage, so that's where that comes from as well. So 4.62 amps RMS, and this means that the current is 4.62 root 2 amps RMS times cos of 60 hertz is going to give us 377 rad per second. So 60 times 2 times pi. If we evaluate that, yep, 377 rad per sec. So 377 T per second plus 1.12. Okay, so there's our current. And now we can jump back up. Now that we have the current phasor, we can figure out the impedance. And that's from V is equal to IZ. So that means Z is equal to the ratio of the current of the voltage to the current phasors. So we can use the RMS values for both. You don't have to use RMS values for both, but as long as you use the same type for both, then you're going to find the right ratio there. So Z is equal to V RMS over I RMS, and that would be 11.23 minus 23.4 J ohms. Okay, and now that we have that, we can figure out what each of the different components would be. So what the resistance value would be. The resistance is just going to be the real part of Z, because the two things are in series, and so that's equal to 11.23 ohms. And to figure out the other part, this is a little bit more involved. What we can say is that the other component has an impedance of negative 23.4 J ohms. So what could be doing that? Well, if we've got a negative imaginary impedance, that has to be a capacitor. And so that's going to be negative J over omega C. So we can figure out that C is equal to this thing, 1 over omega times negative X, where X would be sort of the reactance, the imaginary part of Z. All right. So that means C is equal to 1 over, let's call that W. W times the imaginary part of Z. Okay, and that's 113 microfarad. Great, and these are in series. So we've got our electrical model, we've got the phase angle, we've got the impedance, we've got the current. How would you correct the power factor without modifying how it operates? So this means we have to put something in parallel with it so that it still sees the same voltage. And the idea is that we need, because we've got a capacitive impedance, we're going to need to add an inductor, and we're going to need that so let's just write that down. Add an inductor in parallel such that the complex power that it's using is going to be negative Qj that we're already using. So that's the requirement, and we have that an inductor would use a complex power of Vrms times the complex conjugate of the current that would go through it, which would be Vrms, the same voltage across it, divided by Z of the inductor. Yeah, okay, great. So this is going to be Vrms squared over complex conjugate of Z, which is negative J omega L. Now you notice here I didn't include the bold part, so by that I mean just the magnitude of V. Remember that if you take something and multiply it by its complex conjugate, you get the magnitude of it squared, which is not the same as just squaring the complex number. Okay, so this is supposed to equal, so Vrms squared over negative J omega L is supposed to equal negative Q times J. So this means L is equal to Vrms squared over negative omega Q. Okay. Let's try that out. Vrms squared over negative W times Q. And we've got 76.4 millihenry. Okay. And finally, if electricity costs 10 cents per kilowatt hour, what's the cost per hour to run this appliance before and after the power factor correction? So before the power factor correction, you get billed, well, you always get billed based on the apparent power. Before the correction, it's the magnitude of S, so the apparent power, multiplied by this this rate. So that would be 1 e minus $4 per watt. So it wasn't per kilowatt, so this would be the amount per watt. Okay, and that is, the apparent power was, AP is 554.6, so we're going to get 554.6 e minus 4, which is 0.05546. So 5.5 cents per hour. Then if we've done the correction correctly, then we've got only the real power as the apparent power. So the real power and the apparent power are now the same. And that means we get billed only this 240 watts multiplied by 1 e minus $4 per watt. So that should be, let's 0.024. So about half the electricity bill. That's pretty good. That's something we want to go for.